Good day, third years. In this lecture, we will start with our third module for Physical Chemistry 2. Lecture 3A is all about the thermodynamic description of mixtures. In this lecture, you will understand the effect of composition on different thermodynamic functions, determine the effect of mixing on the Gibbs energy, entropy and enthalpy for perfect gases, and relate the vapor pressure of a substance and its composition in liquid solutions through Rayleigh's law and Henry's law. Let's start with an introduction of the different partial molar quantities relevant in this topic. First is partial molar volume. In your previous lectures, you have learned that the partial molar volume is the change in volume contributed by a unit mole of a substance that is added to a large volume of a mixture. It is given by the equation partial V divided by partial N sub J at constant pressure, temperature, and amounts of the other substance. Looking at this graph on the left, when 1 mole of water is added to a large volume of pure water at 25 degrees Celsius, the volume increases by 18 cubic centimeters. However, when this 1 mole of water is added to a large volume of pure ethanol, the volume increases only by 14 cubic centimeters. This is due to the difference in the volume occupied by a given number of water molecules depending on the molecules that surround them. If water is surrounded by other water molecules, the hydrogen bonds usually hold water at a certain distance. However, when it is surrounded by ethanol molecules, these hydrogen bonds do not form, resulting to a more packed arrangement and thus a lower partial volume of water in ethanol mixture. This example shows how partial volume vary with composition due to changing environment of the molecules. The definition of partial molar volume implies that when the composition of a binary mixture is changed by the addition of a small volume of A and B, or dN sub A and dN sub B, then the change in the total volume of the mixture is given by this equation, wherein we know that partial V over partial N is equal to the partial molar volume of that particular substance. Then we can simplify this given equation to dV is equal to VA dN sub A plus VB times dN sub B. If we assume that the relative amounts of A and B are both increased in a way that will keep the ratio constant, then we can integrate this equation above with respect to N sub A and N sub B with the partial molar volumes of A and B as constant. We then get an equation for the total volume of a binary mixture as V is equal to VA NA plus VB NB. This concept of partial molar quantity can also be extended to any extensive state functions. Let's apply this concept with the partial molar Gibbs energy. You have learned in the previous lecture that the chemical potential is defined as the partial molar Gibbs energy shown in this equation at constant pressure, temperature, and amounts of other substances. By the same line of thinking that we have applied for partial molar volume, it follows that the total Gibbs energy of a binary mixture is equal to mu A NA plus mu B NB, where mu times N is equal or it pertains to the Gibbs energy contributed by that particular substance. Knowing that the chemical potential depends on composition, temperature, and pressure, a more general equation for the change in Gibbs energy when these variables are changed becomes this expression called the fundamental equation of chemical thermodynamics. However, at constant temperature and pressure, the first two terms become zero and the expression becomes a function of just chemical potential and composition. The chemical potential does not only show the reliance of Gibbs energy with composition. It can also be related to other extensive thermodynamic properties using the already established relationships between these properties. For example, if we want to see the effect of composition on the internal energy, we can use the expression G is equal to U plus PV minus TS. Then, isolating the term for internal energy U, we get negative PV plus TS plus G. Therefore, an infinitesimal change in internal energy for a system of variable composition becomes this equation. du is equal to negative PdV plus minus VdP plus SdT plus TdS plus dG. We know from the previous slide that dG is just equal to VdP minus SdT plus mu A dNA plus mu B dNB and so on. Therefore, incorporating that in the equation for the change in internal energy and cancelling like terms, we get du is equal to negative PdV plus TdS plus mu A dNA plus mu B dNB and so on. At constant volume and entropy, we can simplify this equation into an equation that is a function of chemical potential and composition. This follows that the chemical potential of a substance is equal to the partial molar internal energy but under a different set of conditions than the partial molar Gibbs energy. With the same reasoning, we can also deduce that enthalpy and Helmholtz free energy also depend on composition. Now let's go back to Gibbs free energy. In a binary mixture, we know that G is equal to Na mu A plus Nb mu B. Because chemical potentials also depend on composition, an infinitesimal change in composition will result to a change in Gibbs energy given by this expression. dG is equal to mu A dNA plus mu B dNb plus Na d mu A plus Nb d mu B. However, we have previously established that at constant temperature and pressure, dG becomes mu A dNA plus mu B dNb. Therefore, if we combine these two equations, we get Na d mu A plus Nb d mu B is equal to 0. Or in a much more general expression, the summation of Nj d mu J is equal to 0. And this expression is called the Gibbs-DUHEM equation. This equation explains that the chemical potential of one component of a mixture cannot change independently of the chemical potential of the other components. For a binary mixture, if one chemical potential increases, this means that the chemical potential of the other component must decrease. With the Gibbs-DUHEM equation, you will be able to know by how much the other component's chemical potential must change. For example, suppose that the moles of A is equal to 0.22 times moles of B, and the change in composition results in the chemical potential of A changing by negative 15 joules per mole. By how much would the chemical potential of B change? We can answer this question using Gibbs-DUHEM equation. We know that for a binary mixture, the change in the chemical potential of B is equal to negative Na over Nb times the change in the chemical potential of A. Substituting the known values and the given relationship of Na and Nb, we get that the chemical potential of B increases by 3.3 joules per mole. This further shows that if the chemical potential of one component increases, then the other one decreases. The same line of thinking can also be applied to other partial molar quantities, such that we can also say that the summation of the amount N of substance J multiplied by the change in the partial molar volume of J is also equal to 0. For a binary mixture, the change in the partial molar volume of B is equal to the negative Na over Nb times the change in the partial molar volume of A. With the Gibbs-DUHEM equation, the partial molar volume of one component can be obtained from the partial molar volume of the other. Now let us discuss the application of thermodynamics on spontaneous changes in composition, such as that in mixing of two substances. Let us consider two perfect gases in two containers before mixing. The composition of each gas is given as Na and Nb, and both are at the same pressure and temperature. While separated, the chemical potential of these gases is equal to their pure values, which are given by the definition explained to you in the previous lecture. Mu naught is the standard chemical potential of the pure gas at 1 bar. Therefore, we can say that P naught is 1 bar, and we can further simplify this equation to mu is equal to mu naught plus RT ln P, but keeping in mind that P is the numerical value of the pressure P expressed in bars. Before mixing, the initial total Gibbs energy of the separated gases is given by G sub I is equal to Na mu A plus Nb mu B. Substituting the expression for chemical potential from the previous slide, we get this equation. When the partition is removed, the total pressure P becomes the sum of the partial pressures of A and B. The final total Gibbs energy then becomes this expression. Take note that the pressure in the given expression already shows the partial pressures PA and PB. Therefore, the Gibbs energy of mixing is the difference of the final and initial total Gibbs energy, which is given by the equation delta G of mixing is equal to Na RT ln PA over P plus Nb RT ln PB over P. Knowing that the ratio of the partial and total pressures is just equal to the mole fraction and that the amount of substance J is just the mole fraction of J multiplied by the total amounts of the components, we can simplify the given equation above as nRT times the quantity XA times ln XA plus XB times ln XB. Because the mole fraction can never be greater than 1, then ln of x is therefore negative, which makes the Gibbs energy of mixing negative as well. This shows that perfect gases mix spontaneously for all possible compositions because Gibbs energy of mixing is only decreasing. If you refer to the graph on the right, you will see that for any amount of A, the Gibbs energy of mixing is negative. At XA equals 0, which is pure substance B, and XA is equal to 1, or pure substance A, the Gibbs energy of mixing is 0 because there is no mixing that is happening. Using the relationships of the thermodynamic properties, we can also determine the entropy and enthalpy of mixing. For the entropy of mixing, we know that the partial derivative of G with respect to temperature and at constant pressure is equal to negative entropy. Therefore, we can state that the entropy of mixing is equal to the negative partial derivative of the Gibbs energy of mixing with respect to temperature at constant pressure and composition. Knowing the equation for Gibbs energy of mixing, we get the equation for entropy of mixing as negative nR times the quantity XA ln XA plus XB ln XB. Because ln X is negative, it follows that entropy of mixing is positive or increasing for all compositions, as illustrated in the graph on the right. Under constant pressure and temperature, the enthalpy of mixing can be obtained from the equation delta G is equal to delta H minus T delta S. Substituting the equation for Gibbs energy and entropy of mixing, we get enthalpy of mixing equal to 0. This is expected for a system wherein no interactions occur between the molecules of the gaseous mixture. Recall that this is also the assumption made for perfect gases. This means that because entropy of the surroundings is unchanged, the whole driving force for the spontaneous mixing of perfect gases come from the increase in entropy of the system. Let us consider this example. Determine the Gibbs energy, entropy, and enthalpy of mixing when 1 mole hexane is mixed with 1 mole heptane at 298 Kelvin. Treat the solution as ideal. First, we know that the total mole of the mixture is just the sum of the amount of each substance. Therefore, N is equal to 2 moles. And because the substances are equimolar, the mole fraction of both hexane and heptane is 0.5. To solve for the Gibbs energy of mixing, we use this equation. Substituting known values, we get Gibbs energy of mixing equal to negative 3.4 kilojoules. For the entropy of mixing, we know that it is just the negative of the ratio of Gibbs energy of mixing and temperature. Substituting the values for Gibbs energy of mixing and temperature, we get entropy of mixing equal to positive 11.41 joules per Kelvin. We know that the enthalpy of mixing is 0 for perfect gases, and this can also be applied to ideal solutions. It can be checked mathematically using this expression, which results to enthalpy of mixing equal to 0. As an introduction to liquid mixtures, we will also discuss in this lecture how the Gibbs energy of a liquid varies with composition. Let us recall that for a system in equilibrium, the chemical potential of a substance present as a vapor must be equal to the chemical potential of that substance in the liquid. First, let us define some representations. Quantities for pure substances are denoted by an asterisk superscript. For example, the chemical potential of pure substance A is mu A star, or if it is necessary to emphasize that this is a liquid, then the symbol L in parentheses may be added. For a system in equilibrium, we know that the chemical potential of substance A in the liquid should be equal to its chemical potential in the vapor. And from the definition of chemical potential for perfect gases, we know that this is equal to the standard chemical potential of the pure gas plus RT times ln PA star, where PA star is the numerical value of the vapor pressure of the pure liquid in bars. However, if another substance is present in the liquid, say a solute, the star is removed in the equation since this is no longer a pure substance. But take note that the vapor and solvent are still in equilibrium, so this equation stands. Next, we combine the two equations to remove the standard chemical potential of the gas, which then results to this equation. Simplifying the terms with Ln, we get the chemical potential of A in the solution is equal to the chemical potential of pure A plus RT times Ln of the ratio of the partial vapor pressure of A in the solution and its vapor pressure as pure A. In a series of experiments on similar liquids, François-Réault was able to establish that the ratio of the partial vapor pressure of a component to its vapor pressure when present as a pure liquid is approximately equal to the mole fraction of that substance in the liquid mixture. This is described by the equation PA is equal to XA times PA star, and this is called Réault's law. For ideal solutions, the equation for chemical potential of A in the solution can be presented as this expression. Ideal solutions are then defined as mixtures that obey Réault's law throughout the composition of pure A to pure B as illustrated in the graph on the right. This plot shows how the partial vapor pressure of components A and B are proportional to the mole fractions of the components in accordance with Réault's law. Mixtures with components that are structurally similar obey Réault's law very well. So in ideal solutions, both the solute and solvent obey Réault's law. However, for real solutions at low concentrations, William Henry found that the vapor pressure of the solute is also proportional to its mole fraction, but the proportionality constant is not equal to the vapor pressure of the pure substance. Thus, he established Henry's law, which is PB is equal to XB KB, where KB is an empirical constant with dimensions of pressure. As seen in the graph on the right, at low amounts of solute B, the plot of the real solution follows Henry's law more closely than that of Réault's law. Mixtures for which the solute obeys Henry's law while the solvent obeys Réault's law are called ideal dilute solutions. Now let us consider this example. At 90 degrees Celsius, the vapor pressure of 1,2-dimethylbenzene is 20 kPa, and that of 1,3-dimethylbenzene is 18 kPa. What is the composition of the vapor of an equimolar mixture of the two components? Since 1,2-dimethylbenzene and 1,3-dimethylbenzene are structurally similar, we can assume that Rayleigh law applies. We know that the total vapor pressure is just equal to the sum of the partial vapor pressures of the components. And from Rayleigh's law, the partial vapor pressure is just equal to the mole fraction of the substance in the mixture times the vapor pressure of the pure substance. Since they are equimolar, then the mole fraction of both substances is 0.5. Substituting known values, we calculate the total vapor pressure as 19 kilopascals. To get the mole fraction in the vapor phase, we divide the partial vapor pressure of a component by the total vapor pressure. For 1,2-dimethylbenzene, the calculated mole fraction is 0.53, while 1,3-dimethylbenzene, it is 0.47. This ends Lecture 3A. Thank you for listening and see you in our synchronous session.